This is Brian Huffman, and today we will be reviewing a multi-phase fluid analysis using the ANSYS Fluent 2022 R1 package. Surface tension will be a governing flow factor for us today, so we will focus on those options. The structure we have is a micro-electromechanical system. It's an electrical sensor which is manufactured from polycrystalline silicon, a solid. So, the important parts here for us is that we have a solid silicon electrode, the porous electrode, which has holes in it. It is suspended vertically above the substrate, which also contains its own electrode patterning. So in between the porous electrode and the IDE, we have a gap, which can be filled with fluid. Now, how does that fluid fill it? How does it act? That's what ANSYS is here for. So if we take a 2D cross section, we can see normally we have a dry sensor, which is filled with air. The porous electrode has holes, about 6 micrometers square, which allow the fluid, air in this case, to fill the cavity above the IDE, which has a base plane on the substrate. So the suspended electrode will always have some type of anchoring structure, which will come down to the substrate to create these cavities, a porous pocket. That's what we'll call it. So at some time, we will introduce liquid to this structure, and the liquid will come to rest, ideally, and liquid will be permitted into these holes, or it won't. And if it does flow through, how will it flow around the structure? What's the wall shear? Things like that. We can get that from ANSYS. So an actual physical geometry, which is already made, we can see here. So there's a porous electrode with holes in it. The holes allow fluid access to the substrate layer. Now here is a structure which is anchoring the porous electrode to the substrate. So these anchors will impede flow and create distinctive flow patterns. So the manufacturing process for these is standardized. So we have a nominal thickness. So using these nominal thicknesses and the original blueprints for the sensor, we can idealize the three-dimensional computer drawing of these sensors. So using the design modeler feature in ANSYS Fluent, we can design our structure. So a scale model of one of these sensors is shown here in the bottom right. We can see our porous electrode is suspended above our interdigitated electrode. And here are some anchor points, and there is a cavity in between it. This is where our fluid will flow. So let's get Workbench open as you typically would. You can drag and drop a mesh component, which will load up both the geometry and the mesh. So whenever you start this, you need to ensure that you have selected the correct dimension option. Our case here will be 3-dimensional, so that has been selected. So once you get Design Modeler open, I will include these files so you can see them closer and play with them. So once you get into Design Modeler, I started with the solid sensor structures. So you can select a plane, the XY plane, create a sketch, and extrude it as you normally would. So there's plenty of tutorials on this stuff like this, so I will leave that up to homework. So as you go through the design process, you will create solids by extruding them. And to aid our analysis later down the road, I have also sliced the volumes. So, but first, a good point is these are the solid structures. Fluid analysis will take place with the fluid structures. So, once we have our solid structure designed, we can simply create an enclosure, which essentially takes the inverted volume. So anything that was solid will now be subtracted, and whatever is left over, this cavity in our case, will be a new solid, which we can define as fluid. So here's our solids, the originals. Once you made the enclosure, this is the negative, the fluid space. So to help in our meshing, I have sliced the volume into 4 different volumes of constant cross-section. This will help us to structure our mesh and give us faster results with lower mesh counts and more accurate results for surface tension as well. Now, something you should take note of here is on your parts. You can define them as fluid or solid. So these have all been defined as fluid. Just make sure that those are defined correctly. And this is ready to save. Constantly save. Always save. It's your friend and it won't hurt. So let's save this. And we are ready to go to meshing. So let's refresh that. So now we've made our geometry. It's 4 different bodies, which are all considered the same part, the fluid domain. Now going through here is never a bad idea, so go through there, use your curiosity to your benefit. So now remember that I told you I sliced those volumes. So you can select, if you just insert a method and select your bodies, you can use the sweep method. Now this sweep is going to give you perfectly cube elements, quadrilateral, hexahedral. So just using the default is all right. We can mesh it. Now, do you see how fast that was? That is only because we did that to the volumes. And you get a beautiful mesh. Now, before you were to sweep, and honestly, the default method would most likely sweep this because it knows, but it's nice to know the options. So, the only default I changed was the element size. I gave it a 1/4 of a micron. Also, here is your units, so you can change it and do what you will. So a 1/4 of a micron hexahedral elements down here. So that is our element. Now also, Sizing, this is for inflation and for different sizing. So since we have the same size on everything, don't worry about it. Quality is always good to look at. Since we have a perfectly orthogonal mesh, our skewness is going to be low and our orthogonal quality is going to be perfect. So also our mesh count, 83,000 nodes. That's good to keep in mind. A student version of ANSYS can only run about half a million, I believe. So I will include this mesh file as in the literature that I'm providing. Also, while you are in mesh, you need to name. It makes it easier at least. Name all of your inputs and outputs. So here I've used a pressure inlet, velocity inlet, either way. Today we're going to actually use a velocity inlet. Um, we can talk about why these are the same too for this case. So the pressure inlet will be our hole. The liquid will be coming in the negative y direction through this fluid cavity. So you can select the face and name it. Create name selection. Name it as you will. These are special names. You should read the ANSYS Fluent documentation to know these names. These will automatically assign the type of boundary condition. It helps things. I recommend using them. So we have our pressure inlet, our pressure outlet, which will be either side of this. Fluid will flow out, and then the bottom wall. This was just if you want to give different walls different properties down the line, you should name them differently here. But otherwise, just name walls walls. So these would be the bottom substrate plane walls, and these would be the electrode walls. Open domain is a holdover, which should not be there. All right. Now, with our mesh defined, all loaded up, this is all good. Now, one way to do this is to use the Fluent block. You can also just use the Fluent all together with the geometry and mesh. Now, I have found that I don't save properly sometimes doing that, and it corrupts the entire file while you're trying to solve it. So, in my experience, I've found that running Fluent as a standalone application is desirable. But to do that first, you should know that you are able to export your mesh. You will just export the mesh as a Fluent input file, and we will deal with it in the application down the road. So with all of our geometry and mesh set up, let's get our Fluent set up. So once you get in here, you're going to have some options. Try to select them correctly, otherwise it won't like it. So we have a three-dimensional setup. Double precision is recommended for multi-phase. Solver processes use the maximum number of logical cores that are available to your CPU. See your system information for that. Our working directory is where you should save your files. You don't have to, but you should. So we will name a folder as we wish. These are settings for remote computing and custom user functions. We don't need to worry about those. So let's start the program. And now that we are in the matrix, we can load the mesh file that we created earlier. And now as this loads and sounds an alarm at you, you can display our geometry for everybody to love. All right. So here is our geometry. We can see our inlet and our outlet. It's as we expect. There's our beautiful mesh. Now we can run a check here as well. Make sure you don't have any negative volumes, anything too crazy. All right, now that we've got that, don't need to change units, don't need to change display. Scale, we can change to millimeters since we're working in micrometers here, makes it easier. So, this will be a transient flow, multi-phase interface tracking will always be a transient flow. Now gravity is not necessary, but let's do it just for fun. At these small scales, gravity is usually quite negligible. So now that we've got that, let us add a new fluid. Need the properties if we're gonna do an analysis. All right, let's copy these over. Now you can change these and modify them with user custom functions, and that is a whole nother tutorial. So now that we have water and air, our two primary fluids, let us move to models. Viscous. So if you do a Reynolds number analysis for this geometry and use 1 micrometer as the characteristic length, you will get a Reynolds number about on par with the flow speed. This flow speed will not be very high, it is assumed. It's driven by surface tension. It won't go over 10 meters per second. So with a Reynolds number less than 10, we can say it's laminar flow. Now let's come into multi-phase. We will go to volume of fluid. With the volume of fluid, explicit is recommended for this interface tracking. Let's do interfacial anti-diffusion because the water and the air assumed not to mix. Now since we're going to do surface tension, the manual will recommend to you to use implicit body force. Surface tension is added as a body force to our Navier-Stokes equations that we're solving. So let's go in here, define these phases. Something to note, always make sure the heavier, denser liquid is the secondary liquid. That's just how Fluent works. So let's include our surface tension, also able to be defined by a user-defined function. Now the literature will recommend you a value of 72 millinewtons per meter. And also enabling the wall adhesion will give us the contact angle definition ability. No need for those. And let's close that. All right, that's good. Now you can come in here and add some more analyses if you'd like. You know, the energy equation goes along with diffusion. Modal analyses, electrostatic analyses, all sorts of stuff. So, getting to our boundary conditions, let us go. It's nice whenever you're in here to have the actual, it should be named that. Okay. So at our inlet, either way, uh, with surface tension at these levels, if you do an analysis on the forces involved, surface tension will be about 200 kPa. The hydrostatic head is assumed negligible. Hydrostatic head for 3 centimeters of water is about 70 pascals. Just, to keep that in mind. So using a pressure inlet of 0 is the equivalent of using a velocity inlet of 0. That is because the pressure inlet simply takes this gauge pressure, and this is a dynamic pressure. So using Bernoulli's equation, we can calculate velocity from this gauge pressure. I'll leave that for homework. So just to stay true to what we said earlier, we can come in here and change it to velocity inlet. And just make it 0. Normal to boundary makes sense. So we go to the water secondary phase. All volume fractions will be defined in terms of the secondary phase. So volume fraction 0 equals no water. Volume fraction 1 means there will be water sitting directly on top of this opening, pressure inlet, velocity inlet. So now that they are defined there, we can go to pressure outlet. This is your typical setup now. Velocity inlet, pressure outlet. Gauge pressure 0, we have defined that since we have air in this cavity to begin with. This is a atmospheric pressure condition at this outlet. Now, as the cavity fills, we are assuming that the backflow pressure from the rest of the cavity, the pockets surrounding this outlet, the backflow pressure is negligible. So we're just having free flow from the inlet to the outlet. Normal to boundary makes sense. Now, since it's an air atmospheric boundary, initially, we can just leave the backflow volume fraction as 0. If any backflow occurs, it'll be air. We don't expect that in this case, though. So, now with those defined, we can go to our walls. Now at your walls, stationary, no slip, typical boundary conditions. You can define your contact angle. Now this is a modification that occurs to your interface after all your calculations are complete. So the initial calculations occur with a 90-degree interface, and then it superimposes the curvature, that 15 degrees at the wall. That is our boundary conditions. You can leave these Oh, so now that we have our boundary conditions defined, let's make sure. Now, these are some settings that you just have to dive into to know. PISO is recommended for transient solutions. Node-based is a little bit better for interface tracking, and so is 6am, Kicksam, however they say it. So these two are for interface tracking because we want a nice sharp interface as it moves through the cavity, interface between air and water. So for your controls, these are relaxation factors. So starting them off a little bit, 0.7 is recommended by the manual for body forces. Now the other ones, I just start off a little bit lower to aid in this initial solution. So now you can come in to the report definitions and do some volume surface reports so you can get the volume in, volume out, the volume flow rate. Ideally, that's going to be 0 for our continuum assumption. Uh, Checking to make sure that is good is a good idea. Um, so if you guys come in here, you can select volume flow rate, name it however you want. You can come into pressure velocity inlet, and then it'll just give you the volume flow rate. Now I'm saying volume flow rate instead of mass because the mass of water is not the same as the mass of air. So ideally, it'll be a volume balance. Um, you can compute it. So with your report definition, you can also create a monitor, which will, it does it automatically. You can modify your different parameters. You can change the axes, things like that. So doing those is good. Now for this, I'm just gonna tighten up the criteria a little bit. A lot of people will tighten these to 1E negative 6 um, for our tutorial. Let's keep it light. So now that we have a plot monitoring our outputs, oh, you can also do wall shear. That is a valuable resource. So that's available in the same definition procedure. So now that we have all those, let's initialize it. For this, we can just say static water at T0. So X, Y, Z, 0. Water volume fraction, that means we will not have any water initialized anywhere in the domain. So that will all be air. And let's initialize it. Now something which is useful is you can define regions. So any way you want, you can define uh, any of these cells you can define as a region. And by having that as a region, you can also define the volume fraction. So if you wanted this cavity to be halfway initialized with air, halfway initialized with water, you could use a region and define that region as water right here and patch it. So we're not going to do that here, but I've already done it, but let's do it again. All right, it's initialized. So now that we have it initialized, let's go to autosave. This is pretty standard procedure stuff here, guys. So I'm gonna buzz through it. Make sure you're saving where you need to. Every 50 time steps. This is a long solution, so you could even extend it further from there. Depends on how many uh, animation slides you want. So now that you got your autosave hooked up, let's go to contours. Let's go to phases. Fraction water. And there we go. So you can also play with all these different settings, but as the solution goes along, we can define an animation. Now, something that took me a long time to realize, if it's a long simulation, do not save pictures. It will save so many pictures and it will crash your program. So don't do that. All right, now we have our animation set up. Now you can also set it up for pressure, vectors of the velocity, the path lines. Those are all fun, but we just want to see the interface for now. So let's check our case, make sure. So that's because we left it as 0, but it is 0 for our case, so that's all right. Let's do adaptive, multi-phase. Make it an obscene number. Depends on how long you want to run it for, but small time steps are required, so that's why. Global current. There's no reason for it to be 2 there. It asks for problems. Make that a 0.7. You should study that number on your own as to why that's important. Now our minimum time step size needs to go down, way down, because our geometry is small, way small. So now that we have a smaller initial time step, if you go any higher than 1e negative, honestly, yeah, 1e negative 5, your solution will diverge immediately. So it's no good. Now that we have all of our parameters, let's see the solution. Now you can see it flashing here, taking the snapshots. That would be a picture every time if we had done it. Now, since I chose such a small initial time step size and it's adaptive, we will slowly step up to maintain our current number throughout the domain. So eventually we'll reach some sweet spot in time that will allow us to maintain that and go as fast as we can. But right now, see, we're dropping, and this you can change the axis significant digits so that you can read this better. Obviously, this is a pretty low number since everything is 0, so that's good. If you come in here, you can start to see the, if we just pause it, you start to see the flow upset. It's not moving very fast right now, but that is the magic of a transient flow. So with that, you can just let it calculate, Note here, should be pretty intuitive by now, but a volume fraction of 1 is water. That's defined in the color map of our graphics. 0 is air. So Blue equals air, red equals water. Now, if you let this simulation run, you will see the interface of the water come through the cavity, and we will talk about what we get at the end of this solution. Now that we have our results, something also I would like to note about our results. By defining our contact angle, we have essentially defined a static contact angle. Now, this is a dynamic analysis, so that is a little bit of a assumption that the static contact angle is about the average of the dynamic. So just keep that in mind for this as one of the limiting factors here. So you did your solution, you got enough time steps, you saw the animation in your real time was good. So we can come in here and go to CFD post and go to the file folder that has the solution data in it and select the CFD Fluent project. If you're in 2022, if you're in older versions, you sometimes have to load the case separate from the data. So just keep that in mind. It's pretty similar though. But once you've loaded up that project file or case and data files, you will pull in your geometry. So this geometry here is from a larger analysis of the same thing. So up till now, we've only been looking at this fluid domain right here at the very edge. Now, if you, in your design modeler phase, you were to create by mirroring and duplicating the geometries, you can essentially unfold the structure, three-dimensionally to get your entire uh, scale size structure. So once we have our wireframe, we can begin to add contours to it that describe our water volume fraction. So that's just the bottom wall. So this process is pretty similar throughout the board. Something I also like to add, gives it that little extra, is ISO volumes. ISO volumes are fun. So this will color the cells as you wish. So if we color volume fraction, below value, and we say about 0.7, we'll get a three-dimensional rendering that we can color. And actually, instead of using a variable, let's just make it black and white, red and blue, I should say. So now you can see your air bubbles three-dimensionally within your cavity. You can see squashed underneath our porous electrode here, and we're forcing the air out. So if you follow this process, create your contours. You can also come through here and create animations based on time step. You can play with your frame rate, do all sorts of stuff like that. But if you go through that whole process, you can create animations of the fluid dynamics, the flow fields. This is just interface tracking here. So we can see anything below 0.7 as an air bubble, essentially. Fluid is coming in through the inlets with zero velocity. So this is surface tension driven, and the outlets are right here. And we can see our bubbles slowly proliferate out like a nice lava lamp. And that is the surface tension analysis. Now, also we can create charts about the surface tension or the wall shear. So if we go over to that here real quick. So in post-processing, by we have the values available for wall shear at every point in the continuum. So if we define a line along any section of wall, we can plot the wall shear along that line and see how it behaves. So this would be an inlet and an exit where it falls off. But if we come in here to our average values, we can see that this is usually pretty well predicted shear values here. So that can aid in analysis for, particle dynamics around within these cavities. And yeah, so that's useful data, and there is far more useful data within post-processing as well. But as far as interface tracking goes, we were able to visualize the infiltration of the liquid flow within this microstructure and see the interface and its bubbly dynamics filtering through. So I hope this has been helpful, and I wish you the best. Thank you.